Hi everyone, my name is Lando Assistant and welcome back to Assistant in German Academy. In this lesson, we are going to talk about the Euler formula and the Euler identity. This Euler formula and this Euler identity are ubiquitous in mathematics, especially in physics and in electrical engineering. The famous physicist Richard Feynman describes this formula as one of the most remarkable formula in mathematics. The Euler formula is e raised to I theta equals cosine theta plus I sine theta. And a special case of that Euler formula is the Euler identity given by the formula e raised to I times pi plus 1 equals 0. This number 2 formula is oftentimes considered as the most beautiful formula in mathematics because the 5 most popular constants in math, namely the natural number e, the imaginary unit I, the constant pi, the constant 1, and the constant 0 are all tied up together in just one formula. Isn't that cool? So this video is part of the series on Euler formula. In the previous video, we already talked about the Maclaurin expansion of sine of theta. We already talked about the Maclaurin expansion of cosine theta. And we already talked about the Maclaurin expansion of the natural number e. In this video, our task is to prove the Euler formula and derive the special case of the Euler formula, which we call as the Euler identity. And normally, this Euler formula is derived using power series and the Maclaurin expansion of sine, cosine, and the number e. But in our video today, I'm going to use first order differential equation in order to prove this Euler formula. So let's begin recalling how to represent a complex number in a complex plane. So let's draw a Gaussian plane. In this plane, the horizontal axis is for the real numbers and the vertical axis is for the imaginary numbers. If you have a point z on this complex plane, we represent z as a plus bi, where a is the distance from the point of origin going to this point. So this distance is a, and our b is this length. Since b is in the imaginary axis, we write that as bi. So any point on the complex plane can be represented as z is equal to a plus bi. Now, let's draw an equivalent complex polar plane. So in this polar plane, we represent the number z as the distance from the point of origin to that point, which is the radius or the r, and the angle theta. And then to represent our point z, we need to get the equivalent form of this a in terms of the polar coordinate and the corresponding value for b. But we can get the value of this a and this value of b in terms of r and theta by constructing this right triangle. So this side is the adjacent side and this length is the hypotenuse. So if this is a, we can now therefore say that cosine of the angle theta is equal to the adjacent side a over the radius r. And solving for a, we have a is equal to r cosine of theta. Similarly, if this opposite side is b, then sine of the angle theta is equal to the opposite side b over the radius r, and solving for b, b is equal to r sine of theta. Therefore, the form a plus bi now can be written as a equals r cosine theta plus B is r sine theta times the imaginary unit I. Notice that r is a common factor, so we can rewrite this as z equals r cosine theta plus I sine of theta. So in the complex polar plane, a number z can be represented this way. But if you are talking about the unit circle, then the value of r is equal to 1, so z is equal to cosine theta plus I sine theta. We are going to use this value, z equals cosine theta plus I sine theta as our starting point in our derivation of this formula. So the point C in the Gaussian complex plane is equal to a plus bi, but in the complex polar plane, point C is equal to r times the quantity cosine theta plus I sine theta. We are going to begin our derivation of the Euler formula from this value of z when r is equal to 1. That means we are considering a unit circle with a radius of 1. And notice also that in the Euler formula, the right side is a trigonometric function containing the imaginary unit I, and the left side is a complex exponential number. So what the formula says is that instead of adding cosine theta plus I sine theta, we can also find the value of this by just raising the natural number e to an imaginary unit I times the angle. And computing the left side is so much easier than computing the right side. That is the reason why in many applications in circuit analysis, in electrical engineering, in physics, if we use this left side form, the computation is made much easier than using the right side. So in our derivation now, let's begin with c equals cosine theta plus I sine theta. Let's get the derivative of c with respect to the angle theta. So we have dz is equal to d theta. And that is equal to the derivative of cosine theta, which is equal to negative sine theta, plus I times the derivative of sine theta, which is cosine of theta. Now, what's the value of negative sine theta plus I cosine theta? Let's consider again z is equal to cosine theta plus I sine of theta. Now, if I multiply z by I multiply the right side also by I, what we have at the left is z times I equals I times cosine theta, and then I times I is I squared, and I squared is equal to negative 1. So we have here minus sine of theta. And rearranging the right side, we arrive at z times I is equal to negative sine of theta plus I cosine of theta. Notice now that this right side is exactly this right side here. So therefore, dz over d theta is equal to this value, z times I. This is a differential equation that we can solve using separation of variables. So using separation of variables, we can write this as dz over z is equal to I times d theta. Now let's erase this part so we can continue solving that. And from here, let's get the antiderivative of dz over z, which is now equal to the integral of I d theta. Now, what is the antiderivative of dz over z? the antiderivative is ln of the absolute value of z equals I times the antiderivative of d theta, which is equal to theta plus certain constant c. Now, since we do not restrict our domain here to the set of real numbers, then the argument for ln can also be any number. It's not only restricted to the absolute value of z. So therefore, we can just write this as ln of z is equal to theta times I plus c. And then we take the exponential of both sides. That means we use the natural number e as the base, ln z as the exponent, the same thing at the right side. So we now have e raised to ln z is equal to e raised to theta times I plus c. Now, since e and ln are inverse functions, the left side is equal to z and the right side is just copied. Now, we do not know the value of c, but we can assign some initial values for our definition here of z. If you let theta is equal to 0, what is the value of z? So in other words, we want to find what is the value of c sub 0. So cosine of 0 is equal to 1, and I sine sub 0 is equal to I times sine of 0, which is equal to 0. So that means z sub 0 is equal to 1. So the value of z is equal to 1 when theta is equal to 0. So z is equal to 1. Using this initial value, so we now replace z by 1, and we have here e raised to theta is equal to 0, and 0 times I is 0 plus c. And so this is equal to e raised to c. What should be the value of the constant c so that the number e raised to that exponent is equal to 1? We know that any number raised to 0 is equal to 1, so that means our c therefore must be equal to 0. And therefore, we now have the representation of the number z. Z is equal to e raised to I theta plus the value of c equals 0, so we don't have to write that anymore. So we now know what's the value of z. It's e raised to I theta. But what is the value of z? We said that the value of z is equal to cosine theta plus I sine theta. So this is also equal to cosine of theta plus I sine of theta. Notice now that this part that we arrive at, e raised to I theta, is this left side. Cosine theta plus I sine theta is this right side. So at this point, we have just proven that any point on the complex polar plane, z, can be represented as e raised to I theta, and that is also equal to cosine theta plus I sine theta. Now, a special case of this Euler formula is when we let theta to be equal to pi. So if theta is equal to pi, this equation now becomes e times I times pi is equal to cosine of pi plus I sine of pi. Now, what is the value of cosine of pi? In a unit circle, this is 0 angle, pi is here. Cosine of pi is equal to -1 plus I. What is the value of sine of pi? Sine of pi is 0. So we have e raised to I pi is equal to -1 plus 0. And then let's add 1 to both sides of the equation to arrive at e raised to I pi plus 1 is equal to 0. In this form now is exactly the second part here that we would like to prove. And this is now what we call as the Euler identity. So this is how we derive the Euler formula and the Euler identity. There are several ways of proving this Euler formula, and one way is to use the Maclaurin expansion of sine, cosine, and the natural number e. And what is remarkable about this formula is that from complex trigonometric function, we can write that as a complex exponential function with the number e as the base. And this form, e raised to I theta, is found to be a much easier form to compute, and multiplying theta by an imaginary number has an effect of rotating a point on the polar plane. So in our next video, we are going to look at what are some of the applications of this Euler formula and Euler identity. So thank you very much, and we hope to see you again in our next video in this series.